Hello, good evening, students. Just 1 minute, Appa. There is some problem in the pen. Yes, students. Sorry. Yeah. So in the last class, we have studied the energy of an electron in the nth orbit of an hydrogen atom. So what are the formulas? We got it for the total energy. Total energy in the nth orbit is given by minus mz squared e power 4 by 8 epsilon naught n squared h squared. Even epsilon naught squared you will get. Even epsilon naught squared n squared h squared. So this is the formula what you got it for the total energy of an electron in the nth orbit of an hydrogen atom. So for hydrogen, if you are speaking, you can take z value as 1. This clearly tells the energy in the nth orbit is minus m e power 4 divided by 8 epsilon naught squared n squared h squared. What is this negative sign indicates? Negative sign indicates that the electron is bound to the nucleus. In order to remove from the atom, in order to remove the electron from the atom, you require some energy to remove the electron from the nth orbit. So clearly this tells energy in the nth orbit is inversely proportional to n squared. So as orbit number increases, the total energy in magnitude will decreases. But because of this negative sign, you can tell that the total energy also increases with increase in the principal quantum number n. Yes. Look at this. Based on this, now I am going to consider this is the first orbit. This is the first orbit, n equals to 1. Can you tell me what is the energy in this first orbit? You know that n value equals to 1. Mass of the electron, you know it is 9.1 into 10 power minus 31 kg. E is the charge of the electron, that is 1.6 into 10 power minus 19. Epsilon naught value is 8.854 into 10 raised to minus 12. H value is 6.625 into 10 power minus 34. If you substitute all that value, you can get the value of E1 as minus 13.6 electron volt. So this is the energy in the first orbit. Then can you find the energy in the second orbit? Yes. Energy in the second orbit is n is equal to 2. Energy in the second orbit is what? So how the energy and the orbit number are related? Energy in the nth orbit is inversely proportional to square of the principal quantum number n. So you have to divide this value by n squared, right? And this is the second orbit. So for the second orbit, how to calculate the energy by knowing the first orbit energy? It is just E1 divided by 2 squared, that is 4. So E1 divided by 4. So if you divide by that, you are going to get minus 3.4 electron volt. So this is the energy in the second orbit. Now, similarly, can you tell me what will be the energy in the third orbit, n equals to 3? So what is the energy in the third orbit? So you have to divide this by 9. So you'll get approximately 1.54 electron volt. So like this, you can find what is the energy in the fourth orbit. And you can extend this up to infinity. So what is the energy in the infinity? Energy in the infinity will be 0. Energy in the infinity orbit is 0. So whenever the electron is moving from lower orbit to higher orbit, its energy goes on increasing. and the energy comes to be 0 in the infinite orbit. So if n equals to infinity, the energy will be 0. Got it? Yeah. Now, suppose if I consider an electron, which is there in the fourth orbit, let us say, if this electron jumps to the lower orbit, it is going to emit the energy, right? It is going to emit the energy. How to calculate this energy E? For example, it is coming from the fourth orbit to the first orbit. It is coming from the fourth orbit to the first orbit. You just take the difference of fourth orbit energy minus the first orbit energy. So what is this energy E equal to? E4 minus E1. So this is the energy emitted by the electron when it comes from fourth orbit to first orbit. So in general, I'm saying in general, if the electron is coming from higher orbit N2 to lower orbit N1, energy is coming from higher orbit to lower orbit N2 to N1. It is going to emit what? Energy. It is going to emit energy. That energy is given by the formula E is equal to hc by lambda. But what is this E? E is the energy in the higher orbit, that is N2, minus energy in the lower orbit, that is N1. So En2 minus En1 is equal to the energy, that is hc by lambda. So by substituting the energy formulas, if you find what is 1 by lambda, you're going to get finally R into 1 by N1 squared minus 1 by N2 squared. So this reciprocal of the wavelength, is what we called as the wave number, denoted by the symbol nu bar. What is this nu bar? Nu bar tells a wave number. So whenever the electron jumps from higher orbit to lower orbit, what is the formula for the reciprocal of the wavelength? That is 1 by lambda. 1 by lambda is equal to R into 1 by N1 squared minus 1 by N2 squared. What is this R called? R is a constant. That R is a constant called the Rydberg constant. R is a constant called the Rydberg constant. The value of this Rydberg constant is 1.097 into 10 power 7 per meter. But this is valid only for an hydrogen atom. For an hydrogen atom, the value of R is 1.097 into 10 power 7 per meter. Then this is what we have explained here. Actually, this is called the Rydberg constant. What is the formula you will get the Rydberg constant? R equals to m e power 4 divided by 8 epsilon naught squared c into h cube. On substituting these values, because all these are a constant values, by substituting these constant values, we are getting this Rydberg constant. That is 1.097 into 10 power 7 per meter. Please remember that. So Rydberg constant for hydrogen atom I'm talking, that is 1.097 into 10 power 7 per meter. Yes, students, even if you know the orbit number, from where to where the electron is coming, if you know that orbit number, it is sufficient to calculate what is the energy associated and what is the wavelength related to that transition of the electron. Yeah. Look at the same formula, students. So the electron is coming from E2 to E1, that is from N2 to N1. It emits the energy. That energy is given by the formula E2 minus E1. That formula is nothing but r into root of 1 by, into 1 by n1 squared minus 1 by 2 squared. If you just multiply the c for that into z squared, that gives the energy. So if you want the energy in terms of r, if you want the change in the energy in terms of r, you have to tell it is just r times of h into c. R times of h into c. You can find out that in terms of energy also. The reciprocal of this wavelength is called as the wave number. That is nothing but r into z squared into 1 by n1 squared minus 1 by n2 squared. Why I am bringing z squared here? If you are talking other than hydrogen atom, suppose if you are talking other than the hydrogen atom, then you have to write it as z squared into z squared. So whatever the value you are going to get for 1 by lambda, for that you just multiply z squared. If you are not taking the hydrogen, instead of hydrogen, if you are taking a hydrogen-like atom, you have to consider this formula, students. Please be very careful in this. So this is the concept of the energy emitted by the electron when it jumps from a higher orbit to another orbit, that is lower orbit, and the wave number. Got it? Yeah. Before going to this number of spectral lines, you must know what is the concept behind the spectral series. So let us take up the next concept. That is spectral series. Yeah. Now, in order to explain the spectral series, let me consider the first orbit. This is the first orbit. This is the second orbit. This is the third orbit. This is the fourth orbit. This is the fifth orbit. This is the sixth orbit, like this, till infinity. N equals to infinity. Yeah. Now, you know that electron can jump from higher orbit to lower orbit. If the electron is jumping from second orbit to the first orbit, or from third orbit to the first orbit, or from fourth orbit to the first orbit, or from fifth orbit to the first orbit, or from sixth orbit to the first orbit, or if it is coming from infinity to first orbit. If any electron is taking a transition from higher orbit to first orbit only, electron is coming from any orbits, but it is always coming to the first orbit only. Such series is what we call as the Lyman series. So what is Lyman series? So Lyman series is the one where the electron takes a transition from higher orbit to the first orbit. Clear? Yeah. Suppose if the electron is taking a transition from higher orbit to the second orbit. If the electron is taking a transition from higher orbit to the second orbit, then it is called as the Balmer series. If the electron takes a transition from higher orbit to second orbit, then it is called as a Balmer series. Similarly, if the electron takes a transition from higher orbit to the third orbit, it is called as a Paskin series. Then, if the electron is taking a transition from higher orbit to the fourth orbit, then it is called as a bracket series. What is that called? Bracket series. Suppose if the electron is taking a transition from higher orbit to the fifth orbit, then it is called as a p-fund series. Please be very careful, students. If the electron is taking a transition from higher orbit to the fifth orbit, then it is called a p-fund series. Please remember, if the electron takes a transition from higher orbit to the first orbit, then it is called a Lyman series. In this Lyman series belongs to UV region. The Balmer series belongs to visible region. These three, Paskin, bracket, and the p-fund, all these three belongs to infrared region. So please be careful. Balmer series belongs to visible region. Lyman series belongs to UV region. The rest of the three, that is Paskin, bracket, and the p-fund series belongs to infrared region. Infrared region. So this is how the spectral series is going to originate when the electron jumps from higher orbit to lower orbit. So depending on this, please remember, if the electron is coming from 2 to 1, there is only one possibility, right? Suppose if the electron is coming from 3 to 1. If the electron is coming from 3 to 1, it can come directly from 3 to 2, then 2 to 1, or directly from 3 to 1. So how many spectral lines are possible? 3 spectral lines are possible. So to find the number of spectral lines, if you know the orbit numbers, what is the formula you have? Remember this shortcut formula, students? To find the number of the spectral lines, when electron moves from nth orbit to the first orbit, it is n into n minus 1 by 2. If it is moving from n2 to n1, then it will be n2 minus n1 plus 1 into n2 minus n1 by 2. Remember this. Number of electrons, number of spectral lines emitted when electron jumps from n2 to n1 is given by the formula n2 minus n1 plus 1 into n2 minus n1 divided by 2. What is the number of spectral lines when it comes from nth orbit to first orbit? If it is coming from any orbit to first orbit, then simple formula n into n minus 1 by 2. Suppose if it is coming from fifth orbit to second orbit, then you have to make use of this formula. So this is the formula you have to remember, students, to find the number of spectral lines in the hydrogen atom. In the hydrogen atom. Yes. Then come to the Lyman series of the first line. This is the first line, right? This is the first line. The wavelength correspond to the first line you can calculate. Also, you can calculate the wavelength of the last line. Now, you know that the logic, energy is hc by lambda. How energy and wavelength are related, students? Yes, energy is inversely proportional to the wavelength. As wavelength is more, the energy will be the less. Wavelength is more, energy will be the less. So, between the second orbit and the first orbit, the energy is less. If energy is less, the wavelength will be more. So, this is called as the longest wavelength. What is the first line of the series called? First line of the series is called the longest wavelength. The wavelength of the first line is called as the longest wavelength. Then, coming to the last line, students. In the case of the last line, the energy is more. Energy gap between infinity to first is very large gap, right? So energy gap is more. So if the energy gap is more, the wavelength will be less. So for the last line of the spectral series, always corresponds to lesser wavelength. This is called as the shortest wavelength. So in any spectral series, please remember the wavelength of the last line is called as the shortest wavelength, and the wavelength of the first line is called as the longest wavelength. So this is the concept related to the longest wavelength and the shortest wavelength. You have to be very careful in this. Clear? Yes. So this is the spectral series of the hydrogen atom. Any doubt related to this? Okay. So this is how to find the number of spectral series, isn't it? Yeah. So this is the concept what exactly we have studied in the 2 sessions. So this is the brief synopsis of atoms chapter, students. So mainly you have to concentrate on which parameters? The radius, velocity. In this velocity, you have to talk about time period, frequency. Then you have to talk about total energy, both kinetic energy plus potential energy. Then you must know what is the wave number, that is 1 by lambda. Then you must know the concept of spectral series. So these are the scenario, or the synopsis, the basic concepts of the atoms chapter. Yes, students. So let us take up the problems on atoms chapter. Yeah. Look at the first problem. In the Bohr's hydrogen atom, the radius of the stationary orbit is directly proportional to what? Students, what is the formula you have studied for the radius of the hydrogen in the nth orbit? It is epsilon naught n squared h squared divided by pi m z e squared. Correct? No? So what is the radius of the electron in the nth orbit of hydrogen atom? It is epsilon naught n squared h squared divided by pi m z e squared. So clearly this indicates the radius of electron in the nth orbit is directly proportional to n squared. So radius of electron in the nth orbit is directly proportional to n squared. Please remember this. So it is directly proportional to n squared. So option D is the right answer. Now, remember this also. Radius of the electron in the first orbit, if you want, it is called 0.53 angstrom. What is the radius of electron in the first orbit? 0.53 angstrom. This radius is what we called as the Bohr's radius. What is Bohr's radius? Bohr's radius is the radius of electron in the first orbit of the hydrogen atom. So please remember this additional information related to this. So radius is directly proportional to n squared, where n represents the principal quantum number. If you are in the second orbit, then you have to take it as 2 squared times the radius of the first orbit, like that. Yeah. Come to the second problem. In the nth orbit of the hydrogen atom, the energy is given by the formula. What is the energy in the nth orbit they have given? It is minus 13.6 divided by n squared electron volt. Now they are asking you to find the energy required to take the electron from first orbit to second orbit. So where is the first orbit, students? Yes, this is the first orbit. N equals to 1. What is the energy in the first orbit? Minus 13.6 electron volt. Now to where the electron has to take from first orbit? This electron is taken to from first orbit to which orbit, student? Second orbit. So n is equal to 2. So if I put n equals to 2 here, it will become minus 13.6 by 2 square. Minus 13.6 will be the energy in the first orbit. If you want to find what is the energy in the second orbit, you have to take minus 13.6 divided by 2 square, that is 4. That is minus 3.4 electron volt. So what is the energy in the second orbit? Minus 3.4 electron volt. But what they are expecting, the energy required. So what is the formula to find the energy required? Energy required is given by the formula E2 minus E1. What is the difference? Minus 3.4. Minus of minus will be plus 13.6. So what is 13.6 minus 3.4? It is 10.2 electron volt. So how much of energy you have to give to the electron in order to take from first orbit to the second orbit? In order to take this electron from first orbit to second orbit, you have to give a energy of 10.2 electron volt. This is the energy you require to take the electron from first orbit to the second orbit. Yeah, let's come to the third problem, students. In the following atoms and molecules, for the transition from 2 to 1, the spectral line of the minimum wavelength will be produced by. Minimum wavelength will produced by. Students, you know that in order to get a minimum wavelength, what should be the energy? It should be maximum. Because you know that energy is given by the formula E is equal to hc by lambda. Yeah. And also you know that how to calculate the energy in any atom. That is minus mz squared e power 4 divided by 8 epsilon naught squared n squared h squared. So can you tell me how the energy is related to the atomic number Z here? Can you tell me how the energy and Z are related, students? Yes, energy is directly proportional to Z square. Correct, no? Energy is directly proportional to Z square. Yeah. Hydrogen atom means what? 1H1. Deuterium atom means what? 1H2. Uni-ionized helium means what? 2He4. Lithium. Lithium means 3 lithium. 7, no? 3 lithium, 7. So among this hydrogen, deuterium, ionized helium and ionized lithium, for lithium, Z value is more. So Z value is more for which one? For lithium. So Z value is more for lithium. So energy will be more for lithium. If energy is more for lithium, the wavelength will be less for lithium. So if you use which atoms or a molecule in order to get the minimum wavelength, means it should be a diionized lithium. For diionized lithium, the wavelength is going to be minimum, energy is going to be maximum, atomic number is going to be maximum for lithium in the given options. So only the logic behind this is you have to know this. Energy is directly proportional to Z squared, but energy is inversely proportional to wavelength. So based on this, you can tell to get minimum wavelength, the value of Z must be more. In which case you will get more number of Z value, that is diionized lithium. Therefore, which will be the right option? Option D. Yes. Come to this. Energy is there. This is the spectrum they have given, right? Yeah. A, B, C, D, E they have given. A, B, C, D, E they have given. In this transition, they are expecting you to know what is A, B, and C respectively represents. A is coming from which orbit? Look at this. 0 electron volt. 0 electron volt means this is infinity. So this is the last line of Lyman series. So A is coming from the infinity to first orbit. So definitely A should represent the last line, which is also called it as series limit. Last line is also called as what? Series limit. Of which series? Lyman series. So A represents the last line of a series limit of the Lyman series. Now, can you tell me for the transition of B? B is coming from fifth orbit to the second orbit. Second orbit means Balmer series, no. But this is called the first line. This is called the second member. Since it is coming from fifth to 2, it should be the third member of Balmer series. Third member of Balmer series. The third member of the Balmer series. Look at the point C. C is coming from 5th to 3. 5 to 3 difference means 2. So it should be a second member. Second member. It is coming for third orbit, right? If it is coming for third orbit means after Lyman Balmer, which one you are going to get? Pascal. So C must be a second member of Pascal series. C should be a second member of Pascal series. So this is A represents. A is the last line of Lyman series, right? A is the last line of the, look at this. A is the last line of the series limit. Last line of the series, Lyman series. So here they're talking first member, which is not possible. So A is ruled out. They're talking ionization potential of hydrogen. No, ruled out. Series limit of Lyman series, yes. Series limit of Lyman series, yes. Both options C and D are possible. Coming to B, third member of Balmer series. Third member of Balmer series. Third member of Balmer series. Option C, correct. But here it is talking second spectral. So it is not possible. So A represents series limit of Lyman series. B represents third spectral line of the Balmer series. And finally, C represents second spectral line of the Pascal series. So which will be the right option? Yes, option C. Yeah. Come to this particular case. Electron as a mass. It revolves in the orbit of radius 0.529. So this is approximately 0.53 angstrom. So this indicates clearly a first orbit. Yes, it is a first orbit. Then they are asking you to find the linear momentum. What is linear momentum? P. A very quite simple problem, students. You know that the momentum is given by the formula mass into velocity. They have given mass 9.1 into 10 power minus 31. Velocity is given 2.2 into 10 power 6. So what is that momentum then equal to? 9.1 into 2.2. It goes with how much? 10 power minus 31 plus 6 is how much? If you just do that calculation, how much you are going to get? 9.1 into 2.2. It is approximately 20. So 9 to 18, no, approximately it is 20. So this is approximately 20 into 10 power how much? Minus 31 plus 6. That is minus 25. So 20 into 10 power minus 25 is nothing but what? 2 into 10 power minus 24. 2 into 10 power minus 24. So option B is the right answer. Option B is the right answer. Yeah. Come to this. In a beryllium atom, A0 is the radius of the first orbit. Then what is the radius of the second orbit? It's very quite simple, right? Radius of the nth orbit is given by the formula n squared times the radius of the first orbit. Radius in the nth orbit is equal to n squared times the radius of the first orbit. So if you want to find what is the radius in the second orbit, it should be 2 squared times of R1. So R2 will be 4 times of R1. So the formula for the radius in the second orbit will be 4 times of R1. Since they are talking in general, you can go with option C. Option C is the right answer. General formula is n squared times of A0. If you want the particular formula for the second orbit radius only, then you can take it as 4 times of R0. So general formula will be n squared times of A0. Yeah. Yes. Come to this. Very important, students, here. What is ionization potential of the second helium electron? They are talking for which element, student? For helium. Students, you have to be very, very smart in this case. You know that energy is directly proportional to Z squared, right? M Z squared e power 4 divided by epsilon naught squared n squared h squared. You know what is the energy in the first orbit? That is minus 13.6 electron volt. Now they are expecting for helium. This is for hydrogen I'm talking. This is for hydrogen. Can you tell me for helium atom? Helium atom andre ಏನಿರತ್ತೋ? Helium atom means 2 He4. What is the value for Z for helium? Z equals to 2. So what is the energy in the first orbit of helium? From hydrogen to helium, you have to multiply with the Z square. So Z square means 2 square 4. 4 times of 13.6. 4 times of 13.6. Have you got right? Why I am multiplying with 4? Because energy is directly proportional to Z squared. So much you are going to get this? 54.4 electron volt minus. So this is the energy in the first orbit of helium. So whatever the helium is there, for this helium, energy in the first orbit is minus 54.4 electron volt. Now, if there is a electron, in this helium, to remove this electron, how much of energy is required? To remove this electron, how much of energy we require? This amount of energy we require. So to remove the electron from the helium atom, you require an energy of 54.4 electron volt. Energy is 54.4 electron volt. Then what will be the potential if they are asking? If they are asking the potential, you have to tell 54.4 volt. But in the option they are talking about in terms of energy only. So option C is the answer. So instead of potential, you can say it is energy. So what is the ionization energy for helium? 54.4 electron volt. If they are asking potential, then you can tell the potential is 54.4 volts. So this is the ionization energy of the helium. Suddenly don't go with the 13.6 electron volt, students, because you may feel that 13.6 will be the answer. But 13.6 electron volt will be the answer for hydrogen atom, not for the helium. So you have to calculate the energy for helium by multiplying Z squared value. Got it? Okay. Let us move on to the next problem. Let us move on to the next problem. Yeah. Look at this. The energy required to remove an electron in the hydrogen atom they are talking. From which state? From n equals to 10th state. Yeah. So let me write. This is the first energy state. And this is the n equals to 10th state. So what is the energy in the first orbit? Energy in the first orbit is minus 13.6 electron volt. Minus 13.6 electron volt. What is the energy in the 10th orbit, students? You know that energy is given by E1 divided by n squared. If you know the energy in the first orbit, you can find the energy in the nth orbit. What's the formula? E1 divided by n squared. Now, which orbit they are talking? They are talking about the 10th orbit. For 10th orbit, how to calculate the energy? It is divided by 36, I mean hundreds. So 13.6 divided by 100 will be minus 0.0136 electron volt. This is the energy in the 10th orbit. Now they are asking you to find the energy required only to remove the electron from the 10th state. If electron is there in the 10th state, to remove this, what energy you required? We required a energy of minus 0.0136 electron volt. Minus 0.0136 electron volt. So this is the energy we required in the first orbit. Got it? So to remove the electron from the 10th state, what is the energy we required? 0.0136 electron volt. Yeah. Coming to this problem. What's the kinetic energy of an electron in the orbit of radius r with hydrogen atom? But a very good problem, students, but kinetic energy they are expressing in terms of r. We have studied a general formula for kinetic energy, no doubt, but they are expecting in terms of r. They are expecting in terms of r. So what is that? So kinetic energy, actually it is given by the formula of mv squared. Kinetic energy is equal to of mv squared. Now, from the centripetal force concept, from the Bohr's postulate, you know that mv squared by r is equal to 1 by 4 pi epsilon naught into ze squared by rn squared. 1r you can cancel out. So mv squared value will be equal to 1 by 4 pi epsilon naught into e squared by r. Now, why I am not writing z value, students? I am not writing the value of z because they are talking about the hydrogen atom. You know that for hydrogen atom, z value is equal to 1. So this is mv squared value. Therefore, can you tell me what is the kinetic energy? Yes, kinetic energy is half times of mv squared. So half times of, what is mv squared value? 1 by 4 pi epsilon naught into e squared by r. But I will look on the options. In the options, we don't have 1 by 4 pi epsilon naught. Maybe they are talking about CGS system, because in CGS system, 1 by 4 pi epsilon naught value is 1. So, kinetic energy will become what? Half times of this 1 by 4 pi epsilon naught value will be 1 into e squared by r. So if they are not expressing in terms of 1 by 4 pi epsilon naught, you can take that value as 1. So what will be the kinetic energy then? Therefore, kinetic energy value will be equal to e squared divided by 2r. So e squared by 2r. So which will be the right option, students? Option B will be the right answer. Got it? Yeah. Yes. Look at this. Ionization potential is given as 13.6 volt. So energy will be minus 13.6 electron volt. If potential is volt, energy will be in electron volt. then energy is going to be excited by a photon of energy 12.1. 12.1 means it should be in the third orbit. So if it is absorbing a 12.1 electron volt, it should jump to the third orbit. Sir, why it should jump to the third orbit? Yes, there is a reason. You know what is the energy in the third orbit? You have to divide this value by 9. If you divide that by 9, you will get approximately 1.5 electron volt. 1.5 electron volt. So what is the energy in the third orbit? Minus 1.5 electron volt. So if you take the difference from 3 to 1, the difference will be at 12.1 electron volt. So in order to get this 12.1 electron volt, the electron should get a transition from 3 to 1. But they're asking you to find the number of the spectral lines. I've given one particular formula to find the number of spectral lines, students. That is n into n minus 1 by 2. Why I'm using this formula? Because it is coming from higher orbit to the first orbit only. If it is coming from first or higher orbit to first orbit, then you have to use the formula n into n minus 1 by 2. Suppose if it is coming from n2 to n1, then you have to make use of another formula, that which we have studied as n2 minus n1 into n2 minus n1 plus 1 divided by the 2. Since it is coming to the first orbit, you can make use of the formula n into n minus 1 by 2. So put n equals to 3 because it is coming from third orbit. So what will be the number of spectral lines? 3 into 3 minus 1 divided by 2. That is 3 minus 1 will be 2. So 2 and 2 will get cancelled out. So how many spectral lines will be there? There will be 3 spectral lines. So option C will be the right answer, students. So how many spectral lines are there in this transition? In this transition, there are 3 spectral lines. I hope you got these problems. Yeah. So let me continue the remaining problems in the next session, students. In the next session, let me complete this chapter. I will try to complete this. Okay. Yeah. I hope you understood the today's session. Yeah. Thank you.